Good morning. I am Zebulun Arendsee, the founder of Morloc LLC. Today I'll be telling you about our new open source programming language, Morloc. So say you're a programmer and you've developed something cool and you want to share it. Let's say you made a fast multiple sequence alignment program. But if you want a broad user base, you must wrap your algorithm in a heavy infrastructure and maintain it forever. You need to add readers for data in various formats. You need to add data validators, add argument parsers, add dispatch and control code for executing your core functions, add error handling, logging, cleanup, exit code setting, and writers for your different output formats. Then you need to make the tool available as a programming interface, as a command line tool, and perhaps even as a web interface. Through all this, you're documenting, testing, and benchmarking the entire assembly. In this way, much of your time is spent on mundane infrastructure, not the cool algorithms. And worse, you have to maintain this whole system and deal with disgruntled users far into the future. We are working on a cleaner solution. In the Morloc ecosystem, you can write the algorithm in its simplest form in your favorite language. Suppose you've written your own sequence alignment function. Here is the align.h file, a C++ program that implements align as a function from a vector of strings to a vector of strings. Note that the input is not a FASTA file. You don't want to worry about parsing data formats. The interesting problem is aligning strings. Everything else is unnecessary complexity. Also, your users don't want your alignment program to change their metadata associated with their sequences. For example, the def lines in the FASTA. Next, you send your code to Morloc. First, you define a new module named align, load your C++ function, alignment, from your source code, align.h, under the Morloc name align, and export this function. Then you specify the general type of the function. This tells Morloc what the function does. It converts a list of strings to a list of strings. Next, you specify the concrete type, the language-specific type. This tells Morloc how the function works internally. It is a C++ function from a vector of strings to a vector of strings. The type system is a bit too complicated to cover in a 10-minute talk, but has the same type theory foundations as strongly typed functional programming languages like Haskell. Next, you can upload this module to GitHub, and your job as the algorithm programmer is done. Your alignment function can now be built into larger programs, and the compiler will guarantee language interoperability. Now that alignment is loaded into the Morloc ecosystem, you can take advantage of other Morloc-defined functions. The bio module defines I/O functions for dealing with FASTA files. Read FASTA reads in a sequence data as a list of header sequence pairs. Write FASTA will write the header sequence pairs to a FASTA file. These functions may be implemented in many languages, such as R, Python, and C++. It is the role of a compiler to choose the most appropriate implementation and generate any code needed to make it interoperable with our align function. To operate on these lists of pairs, you can use generic functions from the Morloc base package or from other modules. Here are three useful ones. Unzip pair will take a list of pairs and convert it into a pair of lists. With second, we'll take a function and apply it to the second element in a pair, returning a new pair. Zip pair would take a pair of lists and combine them into a list of pairs. With all this, we can define a useful aligner module that Morloc will type check and build into user interfaces. The aligner.lock Morloc script here first imports our align function. Then from the bio and base packages, we import the read FASTA, write FASTA, zip pair with second, and unzip pair from the previous slide. Using these imported functions, we can compose them to define our new functions. Align G aligns all the sequences in a list of annotation sequence pairs. Align G works with generic pairs. This means any form of metadata, not just header strings, can be associated with the sequences. The align function itself is not given the metadata, and so it cannot alter them. After alignment, the metadata will be reassociated with the now aligned sequences. With FASTA, works specifically with FASTA data. It takes a FASTA file input, calls an arbitrary function on it, writes a FASTA file output. Align FASTA combines the last two functions, so we can give align FASTA a FASTA file, and it will create a new file that is aligned. From the command line, morloc can install your alignment module from GitHub, install the base bio modules from morloc lib, build the align.lock script into a command line tool, where the command line tool can print automatically generated help messages. And any exported commands can be run with arguments in JSON format. So in conclusion, morloc unifies languages under one type system, where workflows can be built from simple functions. Functions can be implemented in any language, and these functions can be organized into polyglot libraries that can be shared and tested using common benchmark and testing suites. So if there are any more questions, you can also jump over to morloc.io, and I have a link there to my Discord site where I'm happy to hang out and talk with you all.